This is another quick and dirty little video about stress. This one about characteristics of the stress matrix and the idea of principal stresses. Here's the list of stress components that we encountered in the previous video. It's a 3x3 matrix. The first row of it is related to the stress components that act on the number 1 plane, or the plane that is perpendicular to the 1 axis. And each subsequent row is related to a different face of this imaginary little material cube that exists in the middle of a differential stress field. This list has a diagonal on which we have all of the normal stresses represented. Sigma 1,1 is the normal stress acting on the 1 plane in the 1 direction. The other terms, the off-axis terms, are shear stresses. Here we've represented that same list with square brackets, and this is the form that you would normally see it as you are doing matrix mathematics. The axis, or the diagonal of the matrix, is here represented by a line going through those normal stresses, so that we can focus on the shear stresses for a moment. Now, in the last video, we learned something interesting about those shear stresses, particularly sigma 1,2 and sigma 2,1. We found out that they call them conjugate shears, and that the magnitude of sigma 1,2 must be equal to the magnitude of sigma 2,1 in order for this cube to remain in static equilibrium. When we go back to our little matrix, we see that sigma 1,2 and sigma 2,1 are located right opposite each other across that diagonal line. Similarly, sigma 1,3 must be exactly the same magnitude as sigma 3,1, and they're opposite one another across the diagonal. And sigma 2,3 must be equal to sigma 3,2 in order for that little block to remain in static equilibrium. Since 3 of these components are equal in magnitude to 3 of the other components, we actually only have 6 unique or independent stresses in this list. Here's the little cube that we've been thinking about over the last little bit of time as we work on stress. And that cube exists within a differential stress field. We can represent this differential stress field as an ellipsoid. The long axis of the ellipsoid corresponds with the greatest stress that is imposed upon this little cube. The minor axis, the smallest axis of the ellipsoid, is 90 degrees away from the greatest axis, and it represents the direction of the smallest stress impinging upon this little cube. And 90 degrees away from the greatest and the smallest stresses is an intermediate stress. So this stress ellipsoid has 3 mutually perpendicular axes. It turns out that when our cube is oriented such that the axes of the cube correspond to the axes of that stress ellipsoid, then on the faces of that cube there will be no shear stress. In this stress matrix, you see sigma 1,1, and sharing that first row with it are 2 zeros. So on the 1 face, the face that's perpendicular to the 1 axis of our cube, there is a normal stress, but no shear stress. The same is true of the 2 face and the 3 face. So here's one of those faces, and it has a normal stress acting on it, but no shear stresses. Now that normal stress could be a tensile stress, as we illustrate here, or it could be a compressional stress. But the important idea in these illustrations is the total stress acting on that surface is acting normal to the surface, or perpendicular to the surface. And there are no shear stresses. A surface on which there are no shear stresses is called a principal plane. And the axis that extends perpendicular to a principal plane is a principal stress axis. There are 3 principal stress axes, and in a differential stress state, they're not equal. We call the stress that is coincident with the larger axis of our stress ellipse sigma 1. Sigma 1 is greater than or equal to sigma 2, the intermediate stress, which is greater than or equal to sigma 3, the least stress. Sigma 1 is the greatest principal stress, sigma 2 is the intermediate principal stress, and sigma 3 is the least principal stress. Sigma 1 coincides with the major axis of the stress ellipsoid. Sigma 2 coincides with the intermediate axis of the stress ellipsoid, and sigma 3 coincides with the minor axis of the stress ellipsoid. The principal stress axes are normal or perpendicular to each other and to the principal planes. Any plane in a differential stress field on which there are no shear stresses is a principal plane, and a principal stress axis is perpendicular to it. It's actually pretty easy to start with those 6 stress components we talked about earlier and do a little bit of mathematics and figure out exactly where these principal stress axes are in space and how big the principal stress magnitudes are: sigma 1, sigma 2, and sigma 3. And that's the subject of the next video.